And so lastly, we want to talk about the entanglement requirements for cluster networking, right? What are some of the experiments that we can run, some of the development steps, and what are those key metrics that we'll be looking at for being able to network these QPUs together? So number one, external coupling efficiency, we talked about that. You have to include any transduction that happens. Secondly, entanglement fidelity then across these qubit chip boundaries and the lifetime, the coherence time of that of those states and those gates that are done, and then the qubit data rate for teleportation for entanglement. So you can have a really high fidelity link, but it's a very slow link. That's going to limit the quantum computation that you can do. And so that's where superconducting has some advantages around speed, but they have more challenges around the transduction piece. And we recommend really taking specific development steps to design and understand and then run experiments on transduction so that you can then do the cluster networking. So simulation is an obvious place to start. At Aliro, we have a quantum network simulator that can simulate any photonic device down to the physical optics layer, provides noise models. So this is where we're investing our time and resources to simulate the quantum networking of different QPUs. Then doing a transduction test, of course, to look at that efficiency and teleportation between qubits on different chips. And then finally, when you have a quantum repeater memory that's sufficiently performant and stable, running a test to look at those longer distances that you can do. And so really you need to take those measured steps through and have a plan for how you're going to network these QPUs together. And that difficulty variability of networking is shown here on a plot, showing on the vertical axis networking difficulty from low to high and qubit scalability from left to right on the x-axis. So superconducting are scalable and more mature, but they're more difficult to network because of the transduction needed from the microwave wavelengths. And then neutral atoms and trapped ions are closer to that green circle where we want to be to work on networking and have an expectation of success, which is around having high scalability and maturity, but low networking difficulty. And the photonic is shown here, ready to move into the green circle once we see the scalability, the qubit demonstrations, and the scalability because of the ease of transduction there. Additional metrics, these are not the only two. Networking difficulty and scalability is important, but you need to also look at the circuit depth of your actual quantum device, the gate fidelity, which is composed of the gate fidelity and that gate speed. So keep those in mind as you're looking at where can we expect developments in networking.